Okay, this is Dylan Sieverts. Today is January 17th, and this is for check-in number 2. And I got, let's see here, 9 problems done. Oh wait, no. I got 10 problems done since the last check-in. I was unable to submit my video. I talked with some students and kind of figured out how I should do it, so hopefully this one will go through. I went over number 1 and number 2 in check-in number 1, but I'll just go over them briefly since I can screen record now. So basically, we were given the position function. I'm looking at problem number 1 again, and so I needed to take the derivative of this in order to find the velocity, and from there, from the velocity function, I was able to factor that out and find the time and plug that in to find the exact velocity at those specific x values when the acceleration was at 0, and that was at time -1/2 and 2/3. Then I plugged that back into my original position function to find exactly where that was. Moving on to number 2, we were given the velocity and the initial velocity. So basically what I did is I used a kinematic equation to plug that in to find the unknown k value. From there, I was able to write out the formula for acceleration, but put it in terms of derivative notation, I guess you would call it. I manipulated that and plugged in that unknown k value. And let's see. Then for part B, it asks us to find the time required. So basically I had to write the velocity function in terms of derivative notation, reorganize that equation, and then take the integral of that. And that ultimately gave me some limits of integration from 22.5 to 900. After I took the integral and plugged those in, I was able to get the time required for the projectile to penetrate 3.9 inches into the block. Okay, so that was technically on my first video, but I just reviewed it. Moving on to number 3, it gave us the acceleration function, and we know that that is the derivative of the velocity function to get to that point. So again, I manipulated the equation there on the second line to dv over dt, which is the definition of acceleration. I reorganized that into terms of dt and integrated. Once I integrated that, I plugged in my initial velocity and my final velocity and was able to solve for that. And let's see here. Oh yes, so I solved for my initial velocity and then my final velocity, which I didn't put F final, but that's what that is. And then for part B, I needed to know the speed of the ball when it hits the bottom of the lake, so therefore I had to find the position of basically where it hit in relative to where it was released. And so I did the same thing, put the velocity function in terms of dx dt, manipulated that, took the integral, plugged in my limits of integration, and then was able to find my x value of where that hits. And this one I think I still need to finish, actually. The yellow notes are just notes from videos and such. So I actually need to plug in that x value, which is what I did, and that got me the 12.86 feet per second for part B. I need to review that one and make sure I finish that. Moving on to number 4. This is going to be a really long video. Let's see. So we were given the velocity function again. This is a repeat of the previous question. Put it in terms of derivative notation, reorganize that, take the integral, plug those units in, and was able to find A, the distance the jogger was going to be at after 1 hour, and then same thing for part B is we found his acceleration at time 0 and after 6 miles. So same process for all of those, just plugging in different values from the equations that you solved for previously. Number 5, this one was actually pretty simple. The kinematic equation for circular motion, we're in radian. So the acceleration is negative g r squared over r squared, capital R being the radius of the Earth. So I was able to rewrite the acceleration in terms of the other derivative notation, manipulate that, reorganize it in terms where I could integrate them separately on either side of the equation, plugged in my limits of integration, and found the initial velocity, which was the unknown. And then I was able to plug in the values that it gave me with the radius of the Earth, converted that to meters, and obviously gravity, 9.81, and got the true initial velocity. Number 6, I was able to, this one was harder for me to understand because of the 3 separate pulleys. Took a while to get my head wrapped around this, but basically you just had to write your own equation for the x and y values of where those forces were moving and in which direction. I put my y value in terms of xb instead of yb. So that might be confusing, but basically once I got the equation, k or x equals xa plus 3 yb, I was able to manipulate that to get those terms, like terms on the same side, and let's see. Yep, got them on the same side, plugged in my knowns, was able to get 6 feet per second for the velocity at A where the person was pulling. Then I was able to plug that in to my original equation to get the the acceleration at xb, or at the handle, same thing. Okay, moving on to number 7. Their parachute free falling, I converted everything to meters per second. And for this one, let's see. I did this a few nights ago. Oh, so I got the kinematic equation. V final squared equals V initial squared minus 2AS. And basically was able to plug all of my units in there and get, let's see. I had to solve for time first with VF equals V initial minus AT. Then I plugged my time in to the other kinematic equation I just mentioned and manipulated that and canceled some things out so that I could get the true time, because there were 3 different Y, I guess you could say, positions where the velocity was different. It was 55.6 at the beginning, and then in the middle it was 13.89, and then at the very end it was different. So I had to calculate the time first, and then I was able to use that to find what the total time was during that portion of the free fall or the parachute holding him up. Number 8, I need to come back and finish this one. This one takes forever because you have to take the derivative of this insanely long equation that it gives you. And so basically I just was taking the derivative of each portion of the vector r. So for the I portion or x portion, I took the derivative of the j portion and then the k. I got my velocity function there, and I need to continue simplifying to get that. Once I get that, basically all I do is repeat the exact same process to get acceleration, and that will take a minute to write out and make sure I got all of my algebra correct because I had to redo this one a few times. But yeah, that's 8. I know how to do that. I just need to come back and finish it. Number 9. This one, let's see. So I basically just used another kinematic equation. I looked for the thing that I did not know, plugged everything else in until I just had one unknown, got my max height, which was in the very middle of that parabola from the pitcher to the batter. And then I was able to use that to find yes, the Y final. I found out that that was in between the pitch height limitations between 1.8 and 3.7. And let's see. Well, that was in the middle. And then it was not. Let's see. Oh yeah, so I found Y final, which was the max height, but in order to get that, I had to use it. The X final equals X initial plus V initial velocity T plus 1/2 AT squared. A lot of those components canceled out to a simpler equation, plugged in my units, got time, plugged that into the first kinematic equation I mentioned earlier, got the max height of the parabola, and it does meet the pitch requirements. It's in between those two values. And then to find the height of the pitch at the batter, I had to resolve for t based upon my x distance. Instead of halfway, I went the full 15.2 meters, and then plugged that back into the same kinematic equation. That one's done. Number 10. This one was kind of a process. Basically, since there's no acceleration in the horizontal direction from gravity, there's only acceleration in the vertical component. I was able to use the horizontal kinematic equation listed there and was able to solve independently for all of the inputs of that because my vector is at an angle, so I had to find my x and y components of that. In this case, just x component. And plug that in, I was able to find my time that it took to get to that point at point B, is where I picked. You probably could have done it multiple places, but I picked point B. Then I plugged that into a new kinematic equation that I used in the previous problem, and with my x final, and solved for my v initial velocity in relation to the horizontal distance. Then I was able to repeat the same thing for point C, because I'm trying to find the velocity, or let's see, it asks for, the two different velocities. So I needed to find the velocity at point B and point C to see at what velocity the person had to throw it to get in between those two. So I did the same thing at point C, but obviously there's different x values because the triangle is bigger there. So you have to solve for those unknowns, and obviously add or subtract the difference between the ground. I went from the ground just to make things all the same. And once I got those new x final and y final coordinates, you could say, I just plugged that back into the kinematic equation to get my time it took to get to that point, and then calculated the velocity. And then I got the two different velocities. Number 11, this is a circular motion kinematic equation. Basically just plugged everything in. However, 3Gs is just 3 times the force of gravity from my understanding. So I had to account for that. Number 12 was the exact same, just at 4Gs with different unknowns. So I had to reorganize that equation just to find r instead of velocity. Number 13 and 14 I do need to finish. And I'm sure that I'll do this with check-in 3 maybe. I'm still trying to figure out the relationship between r and theta, and r prime, r double prime, theta double prime, and what those mean. It's been a minute since I've done that, and I haven't really learned that in my math classes or physics. 14, I'm going to draw a force diagram for this one and count all of my pulleys. I think it's going to be a very similar concept to number 6. That's my understanding of it, just with different values. And yeah, that is all. Let's see, time spent studying. Geez, I have no clue. I probably spent 5 hours yesterday watching videos as I did the homework. The homework problems completed, I just went over all of that. Oh crap. Please list and briefly describe problems, not solutions. Okay. And yeah, I worked with Chuck O'Kane in a study group to finish all of the homework. So we watched the E3 and on videos for chapter 11 and the I think 4 and on. I need to write it down next time, but yeah, that's it.